So in this course, we've already looked at the idea that we can find maximum and minimum values of a function over a given interval by checking the endpoints of the interval and checking the possible turning points, which are the critical points. So for example, if I just show you a graph right now, I know that I've got two red lines here. Imagine those dashed red lines are the interval. I know that any maximum or minimum values of any curve, not just the one shown here, the maximum and minimums must either occur at the endpoints of the curve or at the turning points. Okay? In this particular example, you can see that the two turning points that give you the maximum and the minimum. But if I were to say move one of these lines over, then all of a sudden the minimum value, might occur here at the endpoint of the interval. And we check to find maximum and minimum values over an interval. We check the endpoints and we check the critical points. We don't really bother checking to see if the critical points are turning points or not, because that doesn't matter. They're just possible turning points, which means that they're possible maximum or minimum values. So we're going to apply that same logic and that same algorithm, but just with trigonometric functions. The example I've given here is f of x is 2 cos x minus cos 2x over the interval pi over 2 to 3 pi over 2. Now this is actually probably a new notation for you, but this just means that x is less than or equal to less than or equal to 3 pi over 2, greater than or equal to pi over 2. So those square brackets are a shortcut for that. It's sometimes called interval notation. Another example might be if you talked about the interval 3 with notice the parentheses, the curve bracket, 3, 7. That would mean that x is like this. So curve parentheses do not include the endpoint, and square brackets do. So that's a different notation out there just for you to see. Now, of course, finding max and min values, you can't have the curve bracket. It has to be what's called a closed interval. Okay, otherwise the algorithm doesn't work. Because maybe the maximum value happens when you get closer and closer to 3, but if you can't be equal to 3, then you can't actually find that maximum. So anyways, don't worry too much about that. The important thing to notice here is these square brackets. That's what they mean. Okay, so we know that the maximum minimum values of 2 cos x minus cos 2x will occur at any possible turning points, which are any critical points, and at the end point. So we're going to check those endpoints. We're going to check the critical points. So I'm going to find the critical points and the derivative. So the derivative of cosine is, of course, negative sine. So 2 cos x will be negative 2 sine x. Okay, now the derivative of cos 2x is negative sine x, so the negative sine x changes that negative into a positive. We get plus sine 2x times the derivative of 2x using the chain rule, which is just 2. So really we have that f prime of x is equal to negative 2 sine x plus 2 sine 2x. And our critical points will occur when the derivative is equal to 0. The first thing I'm going to do is I'm going to divide everything by 2. So I get negative sine x plus sine 2x. Okay, now we have a problem here. This isn't that hard of a trigonometric equation to solve, but it's difficult to solve for x and 2x at the same time. So we need to remember the double angle identity, which is that sine 2x is actually equal to 2 sine x cos x. So when I apply that double angle identity, I get that 0 equals negative sine x plus 2 sine x cos x. From there, especially because this is set to 0, I can actually factor out the sine x. I'll actually factor the negative sine x out. And I'm left with 1 plus 2 cos x. Sorry, 1 subtract 2 cos x. Okay, which gives me some options. Either sine x equals 0, or 1 minus 2 cos x equals 0, which means that the cosine of x would have to be 1/2. Okay, now When does that happen? Well, there are lots of values where the sine of x is equal to 0. We need to keep in mind, though, that we're only interested in values between pi over 2 and 3 pi over 2. So when would that be equal to 0? If you imagine those angles, okay, pi over 2, of course, is straight up like 90 degrees, and 3 pi over 2 is right here. So we're really only working with these values here, and sine is equal to 0, of course, at pi radians, or 180 degrees. So there's a possibility for one of our critical points is that x is equal to pi. There's one critical point. Okay, well, when is cosine of x equal to a half? Well, if cosine of x is equal to a half, that must mean that we're in quadrant, well, that can't happen here. Between pi over 2 and 3 pi over 2, cosine is definitely going to be negative, since both your values are, your x values are negative here, or you could think of the cast rule if you want, okay? In either case, if we're between pi over 2, and 3 pi over 2, this just doesn't happen, okay? It happens between 0 and pi over 2, okay? But it doesn't happen here. So not possible, not in interval. Not in our interval. If it was, I mean, you'd look at 1, 2, okay, of course, that would have to be root 3, which means this would be pi over 3, okay? But we don't have to worry about that in this case. So with values, we have to check. There's only 3 values: pi over 2, 3 of pi over 2, and pi. So let's do f of pi over 2 is equal to, okay, let's see, what do we have here again? 2 cos pi over 2. Subtract, what was it again? The sine, or sorry, subtract the cosine of 2 times pi over 2. Okay, which is just equal to, well, the cosine of pi over 2 is 0. And this is 0 minus the cosine of pi. Cosine of pi is -1, so we get +1. And then the next value we might try is pi. F of pi is equal to 2 cos pi. Subtract cosine of 2 pi. Okay, the cosine of pi is -1, so we get 2 times -1. And the cosine of 2 pi is the same as the cosine of 0, which is 1. -2 minus 1 is -3. And then our third value we have to check, there's the critical point, is 3 pi over 2. So the other endpoint, f of 3 pi over 2, is going to be equal to the 2 times cosine 3 pi over 2. Subtract the cosine of, look, 2 times 3 pi over 2 is just 3 pi. 3 pi. Okay, cosine of 3 pi over 2 is like cosine of 270 degrees. Okay, that's definitely equal to 0. So 2 times 0, which is 0. Oops. And cosine of 3 pi. So think about 3 pi. You've gone 2 pi, and then you go another pi. You're at 180 degrees, which is the same as pi. It's -1. And so we get +1. So we have our two max values, which are both at the endpoints, and our minimum value. And by the way, when we talk about maximum and minimum values, we would say that the maximum value is 1 and the minimum value is -3. They correspond to points on a graph, but it's really just the y value that we refer to as the max or the min. So we could say, therefore, the max value is 1, okay, and the minimum value is -3. Let's just take a look at the graph for a second. So you can see I have the graph here, and sure enough, there's the graph of 2 cos x minus cos 2x, and we can see that on the interval pi over 2 to 3 pi over 2, the endpoints, sure enough, are our maximum value of 1, and then again over here 1, and then our minimum value of -3. Now you also notice that this graph is periodic. It has a period of 2 pi. So actually, not only could you find the maximum and minimum values on an interval, you could actually find the maximum and the minimum value for the entire graph if you wanted to, because it is periodic. Every 2 pi, it just repeats itself over and over again, okay?
because the cosine of x has a period of 2 pi. The cosine of 2x has a period of pi, but it fits inside two cycles of this fit inside that, which makes it have a period equal to 2 pi. Okay, let's move on to the next example. Okay, so this example is very similar to the previous one, just a different function over the interval 0 pi over 2. So f of x is 7 sine x plus 3 sine cos x. So we'll start by finding the derivative. F prime of x is equal to 7. The derivative of sine x is cos x. Plus, and now notice here we have 3 times sine x cos x. So we're going to have to use our product rule because this function is a product. So I'll start with 3 sine x. The derivative of 3 sine x is 3 cos x. And then we times that by cos x plus 3 sine x times the derivative of cos x, which is negative sine x. Simplify this a bit. I get 7 cos x plus 3 cos squared x, and then minus 3 sine squared x. There we go. Now, I'm going to set this to 0 to find the critical points. So I want to know when it's equal to 0. And I'm left with another trig equation to solve. Now this one's maybe a little more complicated. I only have x. I don't have to worry about having x and 2x, but I've got cosines and sines. Now notice I have a sine squared x. I can actually replace that with 1 minus cos squared x and hopefully get something that works out a little bit nicer. So subtract 3, 1 minus cos squared x. And then my next step is just to simplify this. So what do I get when I simplify it? So just expanding the negative 3 gives me minus 3 plus 3 cos squared x. So now I can see that I have I have 6 cos squared x plus 7 cos x, take away 3. And I can solve this by factoring as well. This is a trinomial. Now if it helps, you can kind of imagine it looks like that. You can imagine it's a lot like 6x squared plus 7x minus 3, but instead of having x, you just have cosine of x. And since 6x squared plus 7x plus minus 3, will factor to 3x minus 1 times 2x plus 3, okay, just using a little bit of trial and error there, that means that I can actually factor the expression of cosines as well. It's going to factor to 3 cos x, take away 1, times 2 cos x plus 3. Which means that one of those factors is 0. Either 3 cos x minus 1 equals 0, which means that cos x is a third, or 2 cos x plus 3 equals 0, which in this case gives us cos x equals negative 3 halves. Now, that is not possible, okay? This can't happen, so we don't need to worry about it, okay? Cosine and sine are always going to be between 1 and negative 1. So it's not possible that it's negative 1.5. So cos x equals a third is going to give us a critical point. Now, let's check. So we know we have one critical point to check. By the way, our interval 0 pi over 2 is all the angles from like 0 to 90 degrees. Okay, so all the trig ratios have one value that exists there. Okay, including cosine of x is equal to a third. Now that's not going to be a special triangle. So we're going to have 3 values to check, the endpoints and our critical point. Let's start with the easy one. Let's start with our endpoint. So f of 0, our first endpoint, is equal to, just got to remind myself, what is this function again? 7 sine 0. And what was the rest of it? Plus 3 sine x cos x, plus 3 sine 0 cosine 0. Now the sine of 0 is equal to 0. Okay, so we end up just getting 0 here. 7 times 0 plus 3 times 0. And then we do the same thing with pi over 2, the other endpoint, which is 7 sine pi over 2 plus 3 sine pi over 2 cosine pi over 2. Okay? So what do we get here? Well, the sine of pi over 2 is equal to 1. But the cosine of pi over 2 is equal to 0. We just get 7 here. Okay, now, how about our other x value? Did you notice here that I didn't actually, so this is a possibility right here. Do you notice I didn't actually figure out what x is? It's going to be some number. I don't know off the top of my head what it is. I could put it in my calculator and solve for x in radians and get some value, okay? And then plug that into the equation. Like, for example, what is that value? If I do it in my calculator, if I make sure that I'm in radians, I'll find that I get about 1.2 radians, okay? But it's an irrational number. And if we use that 1.2 radians for x and put it in the equation, then we're just going to get a rounded answer, which doesn't seem great either. Here's what we can do, though. Notice that I don't actually care what x is. If the cosine of x is equal to 1/3, that means that this value would be 1/3. And I can actually figure out what sine would be. Let me show you what I mean. So when cosine of x is equal to 1/3, I can draw a picture. So between 0 and 2 pi, I know that if cosine of x is 1/3, then that's like having 1, 3, and then I can actually solve for this missing side, which I'll call y. 3 squared equals 1 squared plus y squared. That gives me 8 equals y squared. So y is the square root of 8, which reduces to 2 root 2. More importantly, I know that sine x is equal to 2 root 2 over 3. So when cosine of x is equal to 1/3, it means that sine of x must be 2 root 2 over 3, even if I don't know exactly what x is. And I can look back at my original equation and say f of x is now equal to, 7 times sine x, which is 2 root 2 over 3, plus, 3 times sine x cos x. Again, sine x is 2 root 2 over 3, and cos x is 1/3. So without that x value, even without knowing that x value, I can still figure this out. I'm going to get 14 root 2 over 3 and 6. That's 20 root 2 over 3. I'm sorry. That's not correct. 14 root 2 over 3 plus 2 root 2 over 3, since these 3's here will divide out, which gives me 16 root 2 over 3. Now, if you check with a calculator, you'll find 16 root 2 over 3 is about 7.5, and that actually makes that our maximum value. So this is our max, okay, and our minimum is 0. And we can take a look at the graph too while we're at it. So there's the graph there of 7 sine x plus 3 sine x cos x, and we can see, sure enough, we got our minimum value of 0. Like I said, cosine of x equal to 1/3 happens at about 1.2 radians and about 7.5, which there's your maximum. And then in this graph, this is pi, so pi over 2 is right here, which is about 7, which puts you somewhere in there. So there it is. Not a super exciting graph. But that finishes our second example. We're going to finish this lesson with an optimization problem. One application of finding maximum and minimum values of functions is in optimization problems. In this case, we're looking for the maximum volume of a cone with a slant height of s. Now, there's a few things going on in this. First of all, notice that there are no values. We're just saying any cone, okay? Can we come up with a point at which we know the cone has a maximum volume? So the slant height of a cone is right here, which is different than the height of the cone. It's the distance if you're to walk sort of outside of the cone, okay? And the slant height and the radius and the height of a cone form a right angled triangle as well. We're going to take a trigonometric approach to solving this question as well. So we're looking to maximize, so the first thing we need to know is the volume of a cone is pi r squared h divided by 3. And this is the function we want to maximize. So we want to take its derivative, find the critical point, and at one of the critical points, we will have our optimal value. There's too many variables though, r and h, and we're actually talking about the slant height S here. So let me show you what we're going to do. So I'm going to redraw this triangle from the cone, okay, where this is S, this is H, and this is R. And I'm going to talk about, since I'm taking an approach with trigonometry, I'm going to call this theta here. You probably wouldn't think to do this, but it works out nicely as a solution. And I'm going to look at the sine ratio, and I'm going to say that the sine of theta, or I'm going to notice that the sine of theta is equal to H over S, which means that the height of this cone is really just equal to S times the sine of theta. I can also notice that the cosine of theta is equal to R over S, which means that R is really S times cos theta. So now I have these two equations that I can use for R and H, and they're both in terms of S and theta. I'm going to take those and I'm going to plug them into the equation here so that I can say that the volume of this cone is pi times R squared, which is now S cos theta squared, times the height, which is S times sine theta, all divided by 3. And then just doing a little bit of cleaning this up a little bit, I get pi times S cubed sine theta cos theta over 3. Or as I like to sometimes think of it, pi over 3, since pi over 3 is a constant. Sorry, I forgot to square cos squared theta, sorry. So we square S, we get S squared times X, S cubed, sine theta, cos squared theta. Okay, equals. All right, so one thing that's important to notice here is that, this is the function that we want to optimize. We want a maximum value for this function. We should notice that this is a constant, the whole thing, including S. Because although we weren't given the slant height, we were told that there's a given slant height. So I could have changed this question and said, hey, look, the slant height is 10. Well, if the slant height is 10, then this becomes 10, 10, 10, and it doesn't change the problem. I just chose to say, hey, let's do this for any slant height. So our S is actually like a given dimension of the cone. It is a constant. So we're going to maximize this function. And we want the optimal or maximum value for V. Now you could start thinking about, is there an interval that this function exists on? And there is. You could argue that theta could be 0. If theta is equal to 0, okay, then the height is equal to 0 and the cone has a volume of 0. So that's not an optimal value. I suppose you could argue that theta, the slant, could get as big as pi over 2, 90 degrees. Well, then the radius becomes 0, okay? It's this infinitely skinny cone. And if the radius is 0, the volume is 0 as well. So as theta gets closer and closer to 0 and closer to pi over 2, the volume actually gets really close to 0. So there must be a critical point in between those values somewhere where our volume is a maximum, bigger than 0. So to do that, we look for the derivative, the V prime. Now, because this stuff I've highlighted is a constant, I can actually just leave it out front and take the derivative of sine theta cos squared theta and multiply by that. I'm going to need to use the product rule here. So the derivative of sine theta is cos theta times cos squared theta actually gives me cos cubed theta. Okay, plus, let's see, what do we have here? Sine theta times the derivative of cos squared theta. So the derivative of cos squared theta is 2 cos theta times the derivative of cos theta, which is negative sine theta. And there we have it right there. I'm going to clean that up a bit. And I get cos cubed theta. Okay, I can have minus, let's see, what do I have? 2 sine squared theta cos theta. Just like that. Okay, we're looking for critical points. So V prime equaling 0 is going to happen when all that stuff, this can't be 0, is when all this stuff is equal to 0 here. So when is cos cubed theta minus 2 sine squared theta cos theta equal to 0? When does that happen? Well, we're going to factor out the cos theta. And we get cos squared theta minus 2 sine squared theta equals 0. Okay, so one possibility here for our answers now to solve this is that cos theta equals 0. If cos theta equals 0, that actually means that theta is pi over 2, and the volume is 0. I mean, you can tell right here. Just look at the volume formula we've developed. If you plug in cos theta equals 0, you get a volume of 0. Okay, so that's a possibility, I guess. It's certainly not optimal. Of course, the other possibility, which must be where our answer lies, is in this right here. And how do we solve that? Well, I think what I'll do is I'll express everything in terms of sine. So this is 1 minus sine squared theta. Subtract 2 sine squared theta is equal to 0. And that actually gives me 1 subtract 3 sine squared theta equals 0. Or I could say 3 sine squared theta equals a third. Now notice the sine can't be negative here, not in this example. We can only have values of theta between 0 and pi over 2, where everything's positive, pardon me. So sine theta is just equal to 1 over root 3, which is the same as root 3 over 3. So there we go. There's where our optimal value is going to be. We want sine theta to be equal to root 3 over 3. And we need to think about, well, what is cosine of theta equal to when that happens? So we could say, or cos theta equals, and what we do here is we think about a little triangle, just like before. So sine theta is 1 over root 3. Okay, then this value here is something we can figure out. Okay, root 3, just using Pythagorean theorem. Oh, sorry, root 3 squared equals 1 squared plus x squared. Let's see, that's 3 minus 2, so x would be root 2. So cos theta is actually equal to root 2 over root 3. Just like that, okay? So there is our other possibility. So again, just to break it down, we found the derivative of the volume, okay? We set it to 0, and we said the derivative of the volume function is equal to 0 when sine theta is equal to 1 over root 3, and cos theta is then root 2 over root 3. And then we can look at our volume equation again. So let's take that original volume equation, pi over 3 s cubed, times sine theta cos squared theta. And we've just found that these two values right here and right here, okay, that they are what produces the maximum value. So if I just take them, those values, pardon me, and I plug them into this equation, okay, sine theta root 3 over 3, and cos squared theta. Notice that if cos theta is root 2 over root 3, then the cos squared just eliminates the roots. There's no need to simplify that. I just get 2/3. And let's see, I can simplify that and say the volume will be equal to root 3 times root 2 over 9. 3 times 3 times 3, sorry, is 27. So I get a 27 here. And I get 2 root 3 pi s cubed. And that is my answer. So if someone comes up to you and says, hey, what is the maximum volume of a cone with slant height s? You can say it's 2 times root 3 pi s cubed all divided by 27. Just kind of being silly there. If someone says to you, what is the maximum volume of a cone with a slant height of 10? Well, then you could give a better answer, and you could say it's 10 cubed 1,000 times 2 root 3 pi divided by 27. And there it is. Now, that's definitely the answer. It happens at this critical point right here. In class, we would normally do a lot of questions like this. This is a bit of a weird one. You wouldn't be expected to know how to start this. It doesn't, the idea of introducing the angle right here, theta, at the very beginning, and then using trig ratios, it's not obvious. This is a nice example for learning, but no one would you probably wouldn't think to do it that way. Okay, you'd probably just look at this equation here and think about solving for this, the radius and the height based on the slant height, and not using trig. But using trig, this item actually works out a little bit easier. Okay, that's it for this lesson. Thanks.